This lecture is on the technique of integration called integration by parts, which allows us to integrate certain integrands that we would not otherwise have been able to. And the rule is derived from the product rule. Basically, you start with the idea that the derivative with respect to x of uv, where they're both functions of x, is u dv dx plus v du dx. Multiply out dx's, we get to here, subtract v du over, and we can flip the equation around. So from here to here is simply just symmetric, just flipping it around. Then we integrate both sides. So we have the integral of u dv. We separate these two pieces. So integral of u dv is the integral of duv minus the integral of v du. This part just becomes uv. So the integral of u dv is equal to uv minus the integral of v du. So here's the derivation. You really just want to focus on memorizing this. So integral of u dv equals uv minus the integral of v du. The right side doesn't look simpler than the left side, but the idea is that you would not be able to integrate u dv, whereas you would be able to integrate v du, or it would help you get closer to a place where you would be able to go forward on the problem. So the idea is that generally u differentiates to 0, though not always. Sometimes we go in cycles, as we'll see, and dv has to be something easy to integrate, otherwise what would the point have been? And so that gives you some guidelines for picking u and dv. Also, this is a great thing to memorize. It'll help you decide on what u and dv should be. You want to choose u in this order. So first logs, then inverse trig functions, polynomials, exponentials, and then finally regular trig functions. So you can think of this as Lipit. So you choose u to be whichever one of these comes first, and therefore dv would be whatever is left. It turns out that exponential and trig could be switched, though, as well. Here's our first example. We have x cosine x dx. Note that you can't do a simple u substitution for this. If this were, say, cosine x squared, you'd be able to, but not as it stands now. X is a polynomial piece, cosine is trig, p comes before t in Lipit, and so we'll make u the x, so therefore dv is the cosine x dx. We differentiate u equals x to get du is dx. We integrate the dv equals cosine x dx to get v is sine x. We simply plug it into our integration by parts formula, x sine x minus the integral of sine x dx. Of course, the integral of sine is negative cosine, so the negatives cancel, and we get x sine x plus cosine x plus c. So that's integrating by parts once. Now this is a situation where we have to go even farther. So we have integral of x squared e to the x dx. So x squared is our polynomial piece, e to the x is exponential. Polynomial comes before exponential, so we'll make our ux squared. So therefore our dv is e to the x dx. Differentiate here, integrate here, plug these pieces into our integration by parts formula. So we have x squared e to the x, that's our uv, minus the integral of v du, which is somewhat of a help, and yet we still have integral of x e to the x dx, which requires, again, integration by parts. So x is the polynomial piece, e to the x is exponential, so that goes with the dv, because e comes after p. We differentiate here, we integrate here, and we have our first part from integration by parts, and then we have the second part. And finally we get to something we can integrate from earlier sections. Of course, the integral of e to the x is e to the x, and we get all the way down to here, so that's our answer. Now when you're integrating by parts more than once, and you can imagine this is x to the 7th power, you're going to do it 7 times, we have something called the tabular method, which definitely helps to kind of keep all your information organized. So what you do is you make a u column and a dv column, and we differentiate in this column, we integrate in this column. So I'll differentiate, and then I'll differentiate again, and I'll stop when I get to 0. Over here, meanwhile, I just have to integrate and fill out the rows. And these integrals are all very easy. Generally, you differentiate until you get to 0, or you get a product between the two of some form of what you started with. So we'll see that a little bit later. But if you can get down to 0, that's great, but sometimes you have to stop when you get a form of what you began with. So the diagonal arrow, diagonal arrow, diagonal arrow, and then one coming back horizontally, and then the signs alternate, and this is all just based on the integration by parts formula. It just speeds up the work. And so now we just read off our terms. So this arrow is positive x squared e to the x. So here it is. This one is negative 2x e to the x. This one is positive 2e to the x. And the arrow going back to the left is an integral. So, and that doesn't matter here because of the 0, but sometimes it will. So that would be minus the integral of 0 e to the x, which of course is just 0. This being an indefinite integral, just make sure you add a plus c. And you see that we get the exact same answer either way. This is the tabular method used 4 times for x to the 4th. So you'd have to do integration by parts 4 individual times to do this. So rather than do that, I show the tabular method. We have x to the 4th here. That's our polynomial, our trig sine 2x. Differentiate all these down to 0. Integrate each time here. Every time you integrate, a half comes out because of u substitution, and also we're changing signs occasionally because of the sines and cosines. So you have to keep track of all that. We draw on the diagonal arrows and the one horizontal going back. Start with plus and alternate all the signs, and then you can read off the answer. So plus x to the 4th times negative a half cosine 2x is negative a half x to the 4th cosine 2x. I've got a minus and a minus. The 4 and the 1/4 cancel, so it's x cubed sine 2x, and so on, reducing fractions and canceling negatives where applicable, and finally we get down to the last one, which is an integral of 0 with our plus c. So now we'll see a little trick that we sometimes end up having to do with integration by parts, and also you'll see what I mean by not always getting down to 0. Here we have the integral of e to the x cosine x dx. So what happens is that we make our u e to the x, that's exponential, and our dv is cosine x, that's our trig. So we differentiate, we integrate. So we use integration by parts once, and we get to here. Now we have an integral of sine x e to the x, which is hardly better than cosine x e to the x, but we integrate by parts again, and we get to e to the x sine x. Negatives cancel, so plus e to the x cosine x, and then negatives here, so negative and negative and negative, so minus e to the x cosine x dx. So you see what we have in green. And we have this integral that we weren't able to evaluate, and we have it again. So it seems as if we have accomplished nothing when actually we're almost done. Because we're trying to solve for what this is, what we can do is, realizing it's over here, we add it to the other side, so now we have 2 of them. And then we simply divide both sides by 2, and that gives us an expression for what the integral of e to the x cosine x dx is. So it seems almost like you're cheating, that you haven't really figured it out because you've gone it this sort of back way, but it actually works. The whole point was to find out what this is equal to, and we've managed to basically get an expression for it, which is integrated by integrating by parts twice, adding this piece to the other side because we have 2 of them, and then dividing, put a plus c on the end. Here I show simply that the e and the t could be interchanged. In this case, we could make the u our trig and the dv our e to the x. I've integrated by parts twice. I get down to this green, and the green's the same as the green. And then lastly, just to show how this relates to the rapid repeated integration by parts, the tabular method, excuse me, we see that we have our e to the x here, we have our dv for cosine x, so differentiate, differentiate, differentiate. How do you know how far to go? Well, you know to stop when the product of what you have here is a form of what you start with. When I say a form of what you start with, I mean a multiple of some sort. So this could be 27 e to the x cosine x, or negative 43 e to the x cosine x. Just as long as it's a multiple of what you start with, then you stop. So then we read off e to the x times sine x with a positive, e to the x negative negative cosine x, and then integrate going back. So that's why we have a minus e to the x cosine x with the integral of that. And so we see that we get to the green pieces no matter which way we do this, but in every case you'd always have to add the integral to the other side and then divide by 2 to solve for that final answer. One more example now of seeing integration by parts applied with some other trig formulas, integral of secant cubed x dx. So it's not clear at this point exactly how we split this up. You know, what is the u and what's the dv? Well, we choose dv to be secant squared because it's something we can easily integrate to tan x, which leaves for our u secant x. So we kind of leave the lipid idea aside for this portion. So for our dv is secant squared, our v is tangent, our u then is secant x, and the derivative of that is secant tangent. So first applying integration by parts, I have the integral of secant cubed x is uv, so secant tangent, minus the integral of v du, so secant x tan squared x. This doesn't look all that helpful, but what I can do is use a Pythagorean identity to change tan squared into secant squared minus 1. I distribute secant x and split it into 2 integrals. And now I have a situation similar to what we had in the previous example, where I'm trying to solve for the integral of secant cubed x. I've got another one over here. If I add this to the other side, now I've got 2 integrals of secant cubed x. Is secant x tan x plus the integral of secant x. Finally, the integral of secant is ln secant plus tangent, and then I divide both sides by 2, so that's why this is our final answer. One thing that's interesting to note is that the integral of secant cubed is exactly 1/2 the derivative of secant plus the integral of secant. Here's your derivative, here's your integral, and we have a half of each of them. So that's another way to memorize this, but you should know this process. A couple more examples. Here we have integral of x cubed ln x dx. So ln is a log, so that comes first. That would be in Lipit, that comes first. So u is ln x. So therefore our du is dx over x, which leaves for our dv the x cubed. When you integrate it, you get 1/4 x to the 4th. So it's uv, here it is, minus the integral of v du. And so some x's cancel, and then I can easily integrate this to get to my answer here. If you tried something with the tabular method, you can try to work it out, but it's not necessarily advantageous to do so here. And finally, the integral of arc cosine x dx. So this is inverse trig. It doesn't seem like there's anything else, but what we'll do is we'll call the dx, that'll be sort of our polynomial part. Think of it as x to the 0. So inverse trig comes before polynomial in Lipit, I before p. So we'll make our cosine our u. Here's our derivative. If dv is dx, then b is x. So we have uv, which is here, minus the integral of v du. So minuses cancel, and we have these two together inside our integrand. Then you've got to do a u substitution to integrate down here, and that takes us all the way down to this final answer for the integral of arc cosine x dx.